And welcome back. As we continue our cosmic journey through our own solar system, let's go ahead and take a look at water and the possibility of life on Mars. So when we start talking about the quest for life, Mars, of course, is an excellent candidate for us to explore. Even if it doesn't actively hold life today, it might have in the past. Of all the planets and moons in our solar system, Mars is the most promising place to look for life, both in the form of fossil microbes and maybe some forms of life deeper underground that could still be alive today. But where and how should we actually go about looking for life? Well, we know that the one requirement shared by all life on Earth is that of liquid water. You need liquid water in order to have life. Therefore, our guiding principle in the search for life in accessing habitability in Mars and elsewhere has been to follow the water. If there is signs of liquid water, there is a probability that there might be life. So, if we look at the atmosphere on Mars, the atmosphere on Mars has an average surface pressure of only 0.07 bar, which is less than 1% of that of Earth. The Martian air is composed primarily of carbon dioxide, 95%, with about 3% nitrogen and about 2% argon. Now, you'll notice that the proportions of different gases are like those in the atmospheres of Venus, but a lot less of each gas is found in the thin air on Mars. And while winds on Mars can reach high speeds, they exert much less force than the winds on Earth because the atmosphere is so thin. There's literally less material, less matter for it to push around. The wind is able, however, to loft very fine dust particles in the air, which can sometimes develop planet-wide dust storms. This fine dust then coats almost all the entire surface, giving Mars its distinctive red color. In the absence of surface water, wind erosion actually plays a major role in sculpting the Martian surface, whereas on Earth we have both wind and water to act as the primary eroding force. Now, Mars does, of course, have some clouds that we could talk about. Though the atmosphere has small amounts of water vapor and occasional clouds of water ice, liquid water is not stable under the present conditions on Mars. If you look at Earth, most of our clouds, of course, are nothing more than water vapor and some dust and other particles. Now, low temperatures on the planet and combined with the low pressure means that liquid water still cannot exist on the surface except at the lowest elevations. Water changes directly from a solid state to a vapor without an intermediate liquid state. Now, salty water is sometimes able to exist in liquid form on the Martian surface under the right conditions because the salt actually modifies the conditions of where the water can exist. Now, dust clouds and water ice clouds are able to form on Mars, but these are typically often around mountains. Now, if we look at the polar caps on Mars, we can get, of course, some interesting things. The most prominent surface features on Mars are the bright polar ice caps, which change with the seasons, like the seasonal snow cover here on Earth. The seasonal caps on Mars are composed not of ordinary snow, but of frozen CO2. So they're just like large quantities of dry ice. These deposits condense directly from the atmosphere when the surface temperature drops below about 150 Kelvin. Now, the caps develop during the cold Martian winters and extend down to about 50 degrees latitude by the start of spring. Now, there are, of course, permanent or residual caps that are always present near the poles. The southern permanent cap has a diameter of about 350 kilometers and is composed of frozen CO2 deposits together with a great deal of water ice. Throughout the southern summer, it remains at the freezing point of CO2, 150 Kelvin, and this cold reservoir is thick enough to survive the summer heat intact. The northern permanent cap, though, is, of course, much larger, never shrinking to a diameter of less than 1,000 kilometers, and is composed primarily of water ice. Now, there are, of course, those distinctive channels on Mars itself. There are two geological features that are very prominent on Mars, and they appear to be remnants of ancient watercourses, though a third class suggests maybe intermediate outbreaks of liquid water even today. In the highland equatorial plains, there are multitudes of small, sinuous, twisting channels. These are often referred to as runoff channels because they look what geologists would expect to be from the surface runoff of an ancient rainstorm. These runoff channels tell us the planet had a very different climate long ago. Crater counts show that this part of the planet is presumably about 4 billion years old. So obviously this is quite a distant past here if we're looking at 4 billion years. The second set of water-related features we see are the outflow channels, which are much larger than that of the runoff channels. Many features of these outflow channels convince geologists that they were carved by huge volumes of running water, far too great to be produced by ordinary rainfall. So where could such floodwater have come from on Mars? Well, the regions where the outflow channels originate contained abundant water frozen in the soil as permafrost. Some local source of heating, such as volcanic plains, must have released this water, leading to a period of rapid and catastrophic flooding. You'll note that neither the runoff channels nor the outflow channels are wide enough to be visible from Earth, nor do they follow straight lines. In fact, these things are very much as how would we impact most of our rivers. They wander, they meander, and they're not going to be just cut and dry. The third type, though, is gullies. All right, this is the third type of channels that we are now experiencing. These are the smaller gullies, and they were discovered by the Mars Global Surveyor. On the steep walls of valleys and craters at high latitudes, there are many erosional features that look like gullies carved by flowing water. These gullies, in comparison to the previous two channels, are very young. Not only do we find no superimposed impact craters, but in some instances, the gullies actually seem to cut across recent wind-deposited dunes, which suggests more recent activity. Now, there actually may be liquid water underground that can occasionally break out to produce short-lived surface flows before the water can either freeze or evaporate entirely. So that's leading us to think there might be evidence for liquid water somewhere on Mars. The gullies have the remarkable property of changing regularly with the Martian seasons. Many of the dark streaks elongate within a period of a few days, indicating that something is flowing downhill. It's either typically going to be water or some kind of dark sediment. If it is water, it requires a continuing source, either from the atmosphere or from springs that tap underground water layers. Now, underground water would be the most exciting possibility, but this seems inconsistent with the fact that many of the dark streaks start at high elevations on the walls of craters. And so that gives us the idea, well, if we were to spin back the clock, could we see some ancient lakes and glaciers, and how would that affect us today? Well, there is evidence today of large quantities of ice just below the surface of Mars. So if we could somehow peel back that layer, we could find some ice. In the mid-latitudes, high-resolution photos from orbit have revealed glaciers covered with dirt and dust. In some cliffs, that ice is observed directly. The Perseverance rover is currently exploring a 405-kilometer wide crater Zero, which is a dusty former lake bed and river delta with evidence of large rocks that were deposited by ancient floods. Now, these glaciers are thought to have formed during warm periods, when the atmospheric pressure was greater and snow and ice could precipitate. They also suggest to us readily available frozen water that could support future human exploration of the planet, which is a very exciting prospect because if we have access to water, then that is going to make long-term human habitability on the planet a much more viable option. And of course, we have to, discuss climate change on Mars. Mars probably formed with a higher surface temperature thanks to the greenhouse effect. But as we have seen, Mars is a smaller planet, and it has a lower gravity, which means that atmospheric gases could escape much more easily than that of Earth and Venus. As more and more of the atmosphere escaped out into space, the temperature on the surface gradually fell. Eventually, Mars became so cold that most of the water froze out of the atmosphere, further reducing its ability to retain heat, because water vapor also has some greenhouse gas properties. Now, what happened is, with all this water vapor left, the planet actually experienced a sort of runaway refrigerator effect, just the opposite of what we saw with the runaway greenhouse effect that occurred on Venus. This loss of atmosphere took place within less than 1 billion years after Mars formed, resulting in a cold, dry Mars that we currently can see and observe today.